Now let's move on to section 5 of this notebook, exponential and logarithmic equations. This is by far the most important section here. The reason is because it deals with equations. In order to solve an equation, very typically you'll have to use, well, all kind of things you have learned so far, put them together in appropriate order, and then go ahead, well, one step at a time. That's the way to deal with equations most of the time. They're comprehensive. In this notebook, I'm going to concentrate upon 5 types of problems. One is linear equation of exponentials, kind of like this one. The other is quadratic equation of exponentials, kind of like these three. And then linear equations of logarithm, kind of like this one. And quadratic equations of logarithms, kind of like these three. And finally, number 5, quadratic equations of exponentials of arbitrary base, kind of like these three. Okay, among those, the easiest probably is the linear equation of exponentials, but the reason I put it into problem D instead of A is because this coefficient here are rather complicated. It's okay, let's deal with these. How do you solve this kind of equation? Well, the key is to solve for exponential. Let's call it some other character, y or u, whatever. Solve it, and then take the logarithm to find out what's inside. This is a typical process. Get rid of the denominator by multiplying out 1 plus 25 e to the negative 0.3x to both sides of the equality. Then we have just 500 in the left hand side because the denominator is gone. And the right hand side, 1 times 200 is 200. And 25 times 200 is 5,000. And we have something like that. We are looking for this exponential term. So let's divide and subtract everything away. Before anything, let's divide and make it simple. Dividing by 100, we got some simple equation. Subtract 2 away, then we get, well, we have something like that. And then divide everything by 50. We have 3 over 50. In decimal, it is, let's see, it is 0.06. Well, you can convert it into decimal or leave it like this and then punch the calculator later. It doesn't really matter. In any case, we have a number here, and if we have an exponential, that means we are ready to apply logarithm on both sides. If I do, the logarithm and exponential will just cancel each other. Just go ahead. And then we have the negative 0.3x in the left hand side. Right hand side will be log of 3.50, 3 over 50 here. Okay, we have a coefficient times x is equal to a certain number, so we are ready. Divide away by this negative 0.3, and then this is what we get. Punch in the calculator, and we end up with 9.37 something, I think. Let's see, is that true? 9.37 something, yes, that's right. By the way, this kind of problem is going to be pretty typical when you have to solve a equation regarding a logistic model. And numbers here are going to be rather complicated, kind of like these. That's to be expected. Okay, that was the easiest type, linear equation of exponential. Let's work on some quadratic equation of exponentials, kind of like this one. The key observation here is that e to the 2x power is actually exponential x squared. So this whole thing becomes a quadratic equation, kind of like this. This one is, as a matter of fact, e to the x squared. So we end up with a quadratic equation, and we can factor it. You can use tic-tac-toe method or whatever. Factor it, you're going to get something like that. And setting the first factor equal to 0, you're going to get e to the x is 1/2. And setting the second factor equal to 0, we get e to the x is 3/2. Taking a log of both, we get log of 1/2 and log of 3/2, and those are valid solutions. However, in some cases, we may end up with some extraneous solutions, like the second example here. Well, we make similar observation. E to the 2x, oops, e to the 2x is e to the x squared. So we can factor this quadratic trinomial of exponential, kind of like this. And setting the first factor equal to 0, you get e to the x is 1/2. From the second factor, you get e to the x is -3. Now, do you see e to the x equals to -3, which I just highlighted, is extraneous? Exponential is always strictly positive. The graph of exponential function looks kind of like this. As you can see, exponential is always positive, as you see in this graph. If you have e to the x equals a negative number, that's extraneous. You can clearly see that. Or if you didn't see it, then you end up punching into log of -3. And if you do that, your calculator will spit out an error message. That's another way to see it. But if you artificially simply change it to +3, I've seen some students doing that. That's not right. Every mathematical symbol has its meaning. You cannot change it out of your whim. So just one of them gives you correct answer. So taking the logarithm, you get about, well, this value. Log of 1/2 is precise value, approximately speaking, -0.69 something. Okay, let's move on to the next type of problem. Well, okay, I'm not going to finish this problem because this is pretty much the same as previous type of problem in that this is quadratic equation too. If I kill off the denominator by multiplying the denominators to both left-hand side and right-hand side, we are going to get, well, something like this in the right-hand side. And this gives you a quadratic term of exponential. And moving 5 to the other side, we end up with a quadratic equation of an exponential. So we have to do the same thing. In the end, we may have to deal with some extraneous solution. Indeed, we did. Okay, let's move on to logarithmic equations. We have this kind of problem, which will turn out to be a linear equation of a logarithm. And then we have some quadratic type. Let's do easier one first. A linear equation of a logarithm kind of goes like this. Oh, excuse me, it turns out quadratic as well. I underestimated this problem. Okay, so this 1/2 is moved up to top, so we have log of square root. And then minus log of x. Alright, we can apply log rule here, but what's the point? Move this negative log of x to the other side, and we have log is equal to another log. So we are ready to take exponential of both sides. If I do, then exponential and log cancel out, exponential and log cancel out. We just have the inside. We end up with an equation of this square root function. And solving that equation using variety of techniques, square both sides, solve everything, and then you have to check for possible extraneous solution. We have x equal to -1, plug into the original equation. The first logarithm is okay, but next one, log of -1, that doesn't make any sense. X equals to 2 will turn out to be okay. Plug it into first one, we have log of 2 plus 2, 4. That's okay. This is log of 2, that's okay. Punch into calculator, see if this whole thing is equal to 0. It'll turn out to be a legitimate solution. How about some problem like this one? Okay. Problem A wasn't that simple, to tell the truth, and this one is not likely to be that simple either. So how do we work it out? If you have log equals another log, then we can take exponential of both. But here we have log plus another log on the left-hand side. So it's not that simple. It is necessary to bring it down to a single logarithm in the left-hand side. And this is the key. Apply the log rule and convert the first logarithm into a single logarithm like this. And then convert the logarithm in the right hand side into a single logarithm like this. Now what do we have? If we just disregard this middle part, we have log of x minus 3 times x plus 4 is equal to log of 8. We are ready to take exponential of both sides. If I take the exponential, logarithm and exponential will cancel out, both left hand side and right hand side. We'll just have an equation of the inside. X minus 3 times x plus 4 is equal to 8, and that's a quadratic equation. Easy to solve. Solve it, and we have two candidates, x equal to 4 and x equal to negative 5. Maybe both of them are solutions, maybe one of them is solution, the other is bogus, maybe both of them turn out to be invalid. In that case, you can write no solution. In this particular case, x equal to 4 turned out to be a valid solution, x equal to negative 5 turned out to be an invalid solution. We could find out by plugging in x equal to negative 5 to the original equation, and we ended up with some negative numbers inside the logarithms. You can handle the other problems kind of similar fashion. Take two logarithms in the left hand side as a single logarithm, and the right hand side again move this coefficient off and then just get a single logarithm. How about the third type of problem? Well, we have denominators, so move the denominator to the other side. That's pretty clear. What we do next is a question. If we have just log and then 2 times log, we cannot take exponential right away. Left hand side, log and exponential and cancel out each other. Right hand side, log and 2 times, exponential and 2 times log, that's not going to cancel out. It's very, very necessary to move this 2 upstairs. So we just have log equals to another log. Then we are ready to take exponential of both and simply kill off the logarithm so that we have inside is equal to another inside, equal to the other inside, generating this equation here. 2x plus 3 is equal to 3x plus 2 to the quantity squared, and that's a quadratic equation. In the end, you can factor it and solve the equation, and do not forget to check for extraneity by plugging everything into the original equation. The reason you have to check constantly is because the original equation was not polynomial equation, and if you have other kind of equations like denominator, square roots, or logarithm, the domain is not entire real number system. So some candidates may go outside the domain, and that's something you'll have to check. So the domain concept that I've been emphasizing over and over again, and extraneous solutions that I'm emphasizing over and over again, are intimately related. Now, the hardest type of problems. What if we have a problem kind of like the second one? It is going to be necessary to rewrite everything into the single base so that we have quadratic equation. The key observation you can make is 9 is 3 squared. So 9 to the x power is 3 to the x power squared. And then this one, x plus 2 power, well, it's the same as 3 to the x power times 3 squared, which is kind of like this. 9 to the x power is 3 to the x squared, and x plus 2 power over there can be decomposed into 3 squared times 3 to the x power. And what we have, we ended up with, we have a quadratic trinomial like this. It can be factored. Once you factor, you get, well, two solutions. 3 to the x power is 2, or 3 to the x power is 5 halves. In this particular case, there was no extraneous solution. Just x equals to that, there's one solution. X equals to that, there's another solution. and you can check both are valid.